Hello, people. I expect we are on. That's amazing. Amazing to see you all. Cool. So, mm, let me share this a couple of times. A few more people know. Add it on WhatsApp. Okay, cool. Awesome. Hi, everyone. Sorry for being distracted when we started. Cool. So, I'm gonna look at what we did the last time. Cool. So I'll open the STM32 IDE one. I think so. I think last time we got to a place where we had just done the clock initialization. If I don't remember, no, I'm just gonna check my my comments. Um. So. So the last thing was we added macros to make initialization of a peripheral easier to read. So we added all this device mode, bus configurations, clock speeds, data frame format, polarity, phases, and slave management macros. So I think what we're gonna do today, what I would like to do today, is start implementing SPI in it, so that way we can kind of we can make it so that you can initialize this peripheral and start using it. Cool. So I'll just start from there. Yeah. Also, if you guys wanna join a community and kind of like be able to chat about this or chat about projects you're working on and kind of stuff, in the description there's an invite included for our community Discord, and that should be amazing. It should kind of help us. So I'm just gonna check that the chat is working. Is chat working? Seems like chat is working. Cool. So let's start by implementing SPI in it. Okay, cool. So we've already walked through the functional description of SPI. So I mostly will just talk through the code that I'm working on as I'm working on it. I would really explain much unless there is questions. But yeah, so let's go to the SPI header file, and it looks like we do have SPI in it here. Cool. So and then we go to GPI SPIC. We need to now implement SPI in it. Yeah. I wanna copy. What's this? I would love to make some comments here, just to make sure that we can. Just to make sure that we can. Let's just have documentation comment. So add function SPI init. So that's the function name. So what does this function do? Enables the SPI, the specific initializes a specific SPI peripheral you want to use. Okay, cool. What params? What params are we accepting? I think it's a handle T. Yeah, just a handle T. Params, we'll just do that. PSPI handle and port peripheral handle structure. So are we basically returns void cool. Awesome. So that's done, and there's an extra comment there. We'll scroll a bit. Excuse me. Let's scroll a bit. Cool. Open the comments so I see. Yo, Eric, what's up? Yeah, so let's do SPI implementation. Thanks, Eric, for hanging out. That's cool. That really helps. Always helps to have someone here to ask questions. Okay, cool. So let's go. Too many windows. Okay, cool. Void SPI init. This takes an SPI handle pointer to an SPI handle. Peripheral SPI pointer to SPI handle. Cool. Open that. Let's make a temporary structure, int a temporary 32-bit field register, temp cr1 rec, and then let's initialize that to 0. Cool. And then let's go to the next thing. So let's start by setting the device mode. So are we device mode? So basically, is this peripheral we're setting up? Are we setting it up as a slave or as a master? Okay. So temp cr1 register. Let's set the bits. I think the handle comes. Yes, I handle dot. That's gonna be SPI. Aren't you completing from SPI config dot SPI device mode. Okay, this is gonna be where handle that's why. So you can kind of go through here and delete this and be like dot, and we should get completions now. Let's set in SPI handle. Yeah. In SPI handle. Yeah. No. Why? Just gonna close this file. Go to the header, SPI handle as device mode. Okay, cool. Let's build the project. Just build project so we get auto completion. That's why SPI handle T, SPI handle T. You see handle T as SPI config and reg definite, so I need to find out why this is failing. Sorry. Unknown type SPI handle T. Did you mean GPI handle T? SPI handle T, SPI handle T. Why is this not being found? SPI handle T. SPI handle. Just a moment, guys. Maybe in here I haven't included the just a moment. Yeah, include. That is what I need to do. Cool. So if I include that here, that's gonna fix include just relax. Let's rebuild that. F103. And here I need to rename this file 03. Okay, so I think if we build that, we should have fixed what we were. Sorry, I keep covering my mouth. That fixes one problem. Perfect. Now we go back to implementing the thing that we're implementing in the first place. Okay, cool. So now we can keep on going with this. We need to set the device mode. So let's start by device mode. Cool. Let's set the device mode. So temp reg, temp CR1 reg. Let's set the bits for device mode, which is PSPI handle, and then dot, and then we should get the SPI config, and then in the SPI config we should use device mode, and then we should push this to whenever CR1 says we should. Let's open the. I want to open the manual. Okay, SPI, serial peripheral interface, and then we want to find the SPI registers, and then we want to go to master 2. It's number 2. 0 slave configuration 1. Okay, cool. Okay, 2. Okay, so before I keep going on, I want to segue a bit. This will work. So this should, if I build that should be good. We should have it built. Should be building. Cool. However, check. So every time we mention like numbers here, it's confusing. So what I want to do is I quickly want to pause this, initialization, and go add to the SPI header file and add the bit positions. So I want to add this register, this bit position, master. So like phase, polarity, master. I want to add these positions as macros, and once I add these positions as macros into the code, I should be able to instead of this here saying 2, it should be like go to SPI CR1 master, something like that. I think I can copy this from something else I have, from another piece of code that I've written, just so I don't waste time in this stream, because I'd rather just so I don't waste time on this stream. Let's go here to the header, and then here, and I'm going to define bit positions. Bit positions. So let's look at what I've just pasted in. CR1 0, CR1 phase 0, sepal. So this, if you go into the reference manual, you'll see that I've just copied the bit positions for each one of this. And then I think there's a CR2, and that's the CR2. It's so 0 is RX receive DMA enabled to receive right into memory and all of that, all the way up to, I think that is a TX empty buffer, TX buffer empty, and then the status bits, once we'll use status register. Cool. So now I've added all of that. Now I should be able to come back here into SPI.c and just checking for question. Yeah, cool. So here I should be able to use a macro. I should be able to use a macro here, and you'll magically see SPI CR1 CR1, and then this is master. Okay, so you see how quickly, how easily this makes the code easier to read. Okay, bus config. So this is to set up the bus configuration. Are we in half duplex? Are we in full duplex? Are we in simplex receive only? So I think we can look at that here in the functional description, and we can kind of go see the bus configuration. I think bus configuration, it's easier to read it in the registers themselves. So cool, let's look at it. Bidirectional data mode is so full duplex bidirectional data mode. We have data moving from both sides at the same time. Okay, so, and then half duplex is one is talking while the other is listening, or one is listening while the other is talking. And then there's like simplex, which is like, this configuration is always like, I only send data or I only receive data, and that the combination of that can be set between 3 bits. So bit 15 bidirectional data mode. So 0 is 2 line, so you have 2 lines. 1 is 1 line, but you have both directions of data. And then you have output enabled in case you need to use RX only simplex. So you can disable output, but that means you're only receiving. Okay, and then I think we have the RX only bit to set as well. Cool. So let's quickly walk through the code of this. So it's just setting bits. Okay, cool. Bus configuration. So let's go. Cool. So this is probably gonna be an if. Let's check TSPI handle, and then in here we want SPI config dot I think we want bus configuration, and then we want to say if this is equals to SPI bus config. Let's start with full duplex. So full duplex, let's clear BiDi mode. So full duplex means this should be 0, 2, so 2. So clear BiDi. Okay. BiDi mode. So this should go like temp CR1 reg. Let's set the bit for BiDi. No, clear the bit for BiDi mode. So clear a bit, and then BiDi mode, and then this is 1, and then let's SPI CR1 BiDi mode. Cool. Will this build? something missing? Is it bill? Seems like a bill. Okay, cool. So that's full duplex. Else if, let's deal with the next else PSPI handle dot SPI config dot SPI bus config equals to SPI bus config half duplex. Let's deal with half duplex. So only one line. It's one line, but two directions of data. Cool. Set by die mode. So temp CR1 register, and then let's do a set, and we want to set by die mode, which is 1, and then we want to do SPI CR1 by die mode. Cool, perfect. And then let's do the last, like, if the last PSPI handle, and bus SPI config, and then SPI bus config is equal to SPI bus, but simplex RX only. So let's do that one. So this one will need 2. So we need to clear by die mode. Okay, so we can just literally can copy that, put it here, and then I think we need to set RX mode, RX only. This is receive only. Combining by die mode selects the direction of transfer in 2 lines. Okay, so 0 full duplex, basically don't set it. This is not receive only. 1 output disable. So this is disable output. Okay, this will enable no TX, but still the master will produce the clock. Okay, cool, let's do that. And then here we need to set RX only. Cool. So temp reg temp CR1 reg equals operator. So 1 SPI 1 CR 1 RX only. Cool. So that is bus configuration enabled. Yeah, I mean configured. Okay, so let's configure speed using baud rate. So the speed of, remember, in SPI, data is sent with every pulse. Functional description. In SPI, where is that data transfer diagram? Cool. Data is sampled every time, every cycle. So you need you see, if you basically if you're sampling from the first edge, from the leading edge, the next time when the clock cycles, that's when we send the data. That's when we send data. That's when we data. So with every cycle. So the speed sets how fast the clock cycles. When the clock cycles, we send data. This is going to be mostly defined by the peripheral on the other side, like whatever, like if you have, say, right now I'm working on an RFID thing, and if I want to, the RFID system on a chip is going to come and say, is going to come with a defined speed that it can work in, and my responsibility on this end, on the MCU end, is to set the SPI speed that can work with that microcontroller. Go ahead, cool. Wanna look at questions? None at the moment. Let's jump on PSPI handle. PSI. Isn't, oh yeah. Okay, cool. SPI config, and then let's go. I think it's we should have a baud rate. Oh, it's clock speed. Okay, sorry. And then SPI CR1. I think it's boundary, but it should be BR. Okay, cool. So we've said this configures the speed. Okay, configure frame size. So this could be an 8-bit. You're sending an 8-bit packet, or you could be sending an 8-bit packet, or what's the other packet? What am I asking? Or a 16-bit packet. So let's configure what we use. This is temp CR1. Okay, temp CR1 reg, and then let's set the frame size. PSPI handle, SPI config dot data frame format, and then this will be SPI CR1 I think DFF. Cool. Data frame format, so that's in. Configure cpol, I think. Okay. Temp CR1 reg. Okay. And then we're gonna do PSPI handle. SPI config dot cpol. Okay, clock polarity. SPI CR1. cpol is done. Configure clock phase. So are we using leading edge or trailing edge? SPI handle. Okay. SPI config. SPI. CR1. Okay, cool. So this actually is all the work that we need to do. To implement SPI in it, I would say. Let me think about it. Do we need to do anything else? Really? I think we need to do SSM, slave management. Configure SSM, slave management. So temp CR1 reg, PSPI handle, SPI config dot SSM CR1. Okay, let's first begin by we'll get there later. PSPI handle. So let's set, now that we basically filled this temporary register, this temporary 32-bit field, I think it's a struct, with the configurations we want for our SPI peripheral. So now the thing I would do is PSPI handle, and then I would go into the peripheral the peripheral itself, and then I would go into the register, which is CR1, and then I would set this register as temp reg CR1. Cool. So that concludes setup. I think so. Cool. Quickly before before we implement SendData, I think we should also throw in deinit. So just remember, when you want to save, when you want to write applications that are efficient, you want to like turn on the peripheral, use it, turn it off. So you should always have a deinit or a reset possibility. That way you can always save power and kill the I'll just go to the header file and copy it. SPI, I'm just SPI deinit. SPI deinit. So you want to at least be able to kill the peripheral when you're not using it. Not kill it, disable it. Okay. You want to disable the peripheral, de-initializes. Takes a handle. I think it takes a SPI X address, because from there we can just do all the setup. Okay, void SPI d init SPI reg def t. This is a pointer PSPI X. One of the SPIs could be 1 or 2 or 3. If PSPI X is equals to SPI 1, SPI 1 reg. We actually made these macros in the last stream, so there should be PSPI X go to SPI 2. That's SPI 2 reg reset. If SPI X is equal to SPI 3. Okay. SPI 3 reg reset. Boom. 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 Okay, so let's build that. What? It builds. So cool. So that means it probably will work. Okay. Posing for questions as I try and commit this code. And then we can go on. We can go on to implement SendData API. SD workspace, my workspace, target, STM, yeah, git status, git add drivers. Git commit dash v, that's the right rather. Implement SPI init and dinit, dinit, add macros for SPI bit positions, include SPI header in MCU header. Cool. So that's already up for you guys. Pull it, use it. Cool. So we've implemented SPI init, we've implemented SPI dinit. I think the next thing we're gonna do 30 minutes in, 40 minutes in. So probably do another 20 minutes of implementing SendData. And then I think we can, from next time, we can start by testing SendData. And I'll have, I need to go and get a bigger breadboard, bigger than this, so that I can have this guy and this guy on the same breadboards. And once I have both of them on the same breadboards, I can send data between them using SPI. So I think for today, let's quickly throw in SPI init, SPI SendData, and then we could probably go from there. Cool. Okay, so in order to do so, this is, let's briefly run through the transmit sequence, or maybe how to send data. Okay, cool. So number one, select the BR, which is what we already did. That's to set the speed. Select the CPOL and C phase bits. Set from frame format. Configure LSB fast. Ooh, we did not do that. So that can, I think, SPI header. Do we have LSB fast? I wonder. Do we do we need to include we'll add that later. We will add that later. Cool. We can add the thing later, but let's see. Let's look at the description. So we need to configure LSB fast. Let's throw it in. Okay, throw it in now. Throw it in now. SPI header. Int 8 underscore t SPI LSB fast. Okay, LSB fast, and then we need to go to SPI.c and let's add another one here. Configure LSB fast. Okay, cool. Temp 01 register. PSPI handle. SPI config. LSB fast. And then we want to do that. Send that to SPI 1 LS fast. Cool. So we've configured that. Okay, cool. We've added that, and we can actually just go to git status, git add drivers, git commit. That's up. That's up for you guys. Okay, cool. So let's go back to reading the description that we're asking. If the NSS pin is required, in input mode, in hardware mode, connect the NSS pin. This is just describes it. We will do this later. The master and SPE bits must be set. They remain set only if NSS pin is connected to a high frequency. Okay, cool. We'll get to that. Transmit sequence. The transmit sequence only begins when a byte is sent to the TX buffer. The data is parallel loaded onto the shift register from the internal bus. You don't have to do anything with this. You do not have to deal with loading or unloading of the shift register. During the fast bit transmission, then shifted out serially to the MOSI pin, MSB fast or LSB fast, depending on the bit, and CR1. The TXE flag is set on the transfer of the data from the TXE buffer to the shift buffer. An interrupt is generated if a TXE IE bit in the SPI CR2 bit set. So first of all, I think let's add the flags. We need some flags. When receiving and sending data, we need flags so that we can use them to, how do I say? When receiving and sending data, we need flags so that we can use them to check whether data has been sent or not. Okay, so let's define some flags in our header file. Okay, SPI flags. Okay, define SPI TXE flag, and then this should be, it should be 1, and then SPI SR TXE. Okay, cool. That's number 1. Let's define the flag TX buffer is empty. Okay. RX buffer, SPI RX buffer is not empty flag. So you have data incoming. The TX is empty, the data you sent has been completely sent. SPI SR. This is RXNE. RX not empty. Okay, cool. We'll look at these flags just now. Define SPI busy flag. We'll go to the reference manual right now and just look at these ones. If you have any questions, please do. And then let's go here and say SPI SR busy. Okay, let's quickly go look at these 3 flags so that we see what they do, and then we can come back to implementing. So if we go to SPI registers and we want to go to the SR register, the status register, so the busy flag, this flag is set and cleared by hardware. Basically, is it busy or not? Okay, and then we'll get to all of these other ones later, but for now we're just using this one or not. Okay, so we have transmit buffer empty. The data you gave us, we've already sent it. Receive buffer not empty. Something has come in. We have received some data. Okay, and then below here, let's probably define a function to check the status of a flag. Int 8t. This returns a 8-bit integer. SPI get flag status. So this will take in an SPI address. It will take some peripheral. So regdeft, the address, and then PSPI Okay, so this is the thing itself, and then in the other you int put it in flag, so flag. So which flag do you want to, which peripheral, SPI 1 or 2 or 3, which flag, TX, ERX and ER or not. Okay, cool. So that's the beginning of that one, and then probably need to let me go, oh, that's fine, that's okay. Okay, cool, that's fine. That was confusing. I want to go to my MCU header file, and I want to add I want to add some macros here. Define flag set. This is set define flag reset. This is reset. So basically we're adding macros so that whenever we need to do something that is, we need to set or reset a flag, we can do that in a way that is readable. You can set it straight to you can set it straight to off or on, but that might sometimes be difficult to read. So if I just look at some code and this code is just going straight to it's just going straight to it's just setting a bit, or like it's just setting 1, but what is 1 meaning? So now I've added some code to enable us to use we're using a macro so that we can read the code easier. The code is very little, but if you add enough macros, someone can read the code. Okay, cool. So let's implement. Oh, cool. So we were reading this. We were reading the functional description. Okay, cool. There's a transmit sequence. Okay, so this is, let's do it, master. Okay, data is parallel into all of this. So we actually stepped out to implement the flag. So let's implement SPI SendData. Okay. Is there in the SPI H, do we have SendData? Cool, we have that guy. Okay, and then if I come to SPI.c, let's come here, put that there. Let's make a brief at fn SPI send data. I'll just check comments for any questions. No questions so far. Cool. SPI send data, and then I'll go into at brief. Let's say this is a blocking API for sending data of SPI. Function this waits until transfer is complete. Okay, cool. So that's why it's blocking. We're not using interrupts yet. PSPI SPI X, the peripheral to use. Okay. Let's see. So PTX buffer outbound data buffer data itself, probably the length of the data we want to send, length perfect. Okay, cool. So that's what we're gonna send, and that's how it's gonna work. Basically, those three parameters are like which peripheral, how much data, from where. So I have, let's say I have a book. I have a book of words. From this book of words, pick 10 words and send them using this peripheral. So the buffer is the book of words. The length is how many words, or rather in this case bytes. And then the PSPIX is the peripheral. Okay? Cool. Okay, so here comes the waiting part. While len is more than 0, let's keep looping. Okay, and then let's now implement the data. So wait for TXE to be set while we need to implement this SPI get. Okay, so first of all, let's go to our let's add oh yeah, we did define this get status flag. So let's perhaps implement that one first because we're going to use it, and then once we do that, we can come back and finish this function. Okay. So at fn SPI get flag status. Okay. At params is PSPIX, which is the address of the peripheral in use at params flag name okay, the name of the flag whose status we want. Just one break. Sorry, I'm gonna take a water break. Okay, returns work. Cool, cool, cool. Let's implement this. You int 8. No! No one's correcting 8-bit integer. So that way we can know if it's false or true. Okay. Returns, it does return the status of the actual flag that we were talking about. 8 T. Cool. SPI. Get flag. Status. Yeah. H. FT. Yeah. Okay. If P Okay, so this is quite easy to read. We're using a bitwise AND operator to check we basically picking up the whole status register and checking the flag name. If you remember when we were defining the flag names here, we did some data setting. So we're using the calculation of this. So the status register and the flag name that we've just computed should be true. If they are true, then the flag is set. If they are not true, then the flag is not set. So when we're doing get flag status, so now let's do SPI get flag status, okay, and PSPIX is the PSPIX we have, and then we want the TXE is TXE empty, okay. TXE flag. Let's check whether this is equal to int. No, something wrong. I want to build this to see what the problem is. Oh, we are past 1 hour. Amazing. seems my flag definition is wrong. In my macro definition, I seem to have added some. My macro definition has this. That's not supposed to be there. This is not supposed to be there. Yes. Build. Okay, now it's building. Now it's building. Cool. So wait for TXE to be set. What does TXE being set mean? TXE being set means the transmit buffer is empty. So you can, the transmit buffer is empty, which means I can get, you can send more. Okay, so now let's send data. Check DFF. So if DFF is 8, we take 8 bits and send them. If DFF is 16, we take 16 bits and send them. But we also like minus. We also have to decrement the length as well as we're doing this. SPI CR1. CR1, and then we want to do is the LS is the data bits, is the DFF bit set. SPI CR1. DFF. And that's it. If that is set, then which means we're sending it's in 16 bit. This means this is 16 bit data format. So okay, PS IPX. And then here we're gonna do the data register. Okay. And then here we're gonna do, we're putting data into the data. We're putting 16 bits into the data register. If that is not the int 16t, and then we want to do that, and ptx buffer, cool. And then what we want to do is decrease the length. Decrease len twice, since we picked 2 words, something like that. So len minus len minus, okay. And then increment data pointer location, if that makes any sense. So okay, let's now do the same thing else. This is 8-bit frame format, SPI DR TX buffer, then minus just once, okay, PTX buffer, okay, cool. So I hope this makes sense. We've implemented SendData, and we've added get status flag. There is still a fit. There is still we still need to do quite a few. Let me just commit this. I'll look at Is there any comments yet? No. So okay. Push force. That's fine. Git status. Git add drivers. Git diff dash staged. Git commit. Define SPI flag and flag states. Git status. Git add drivers. Always git commit. Git diff dash staged. Git commit dash implement send data API. Okay, cool. So before we keep going on with this, there's a couple of things I think we've missed. Whenever we're using SPI, there's a few things that need to be set. SSM needs to be set. SSOE needs to be set. This is for when we're using NSS or not. And then also, if you look at the SPI registers, I just realized, if we look at the SPI registers, so let's look at SPI01 register. There is an SPE. We have to set SPI enabled or disable before we can use it. So the other thing is we have to add SPI. Let's add peripheral control. Let's add peripheral control, and let's add a couple of APIs to control the peripheral. Cool. So a couple of SPI. Let's add some some APIs. Risk APIs. Okay, so let's add this too, and I'll explain them quickly. So number one, we'll add SPI peripheral control. This is this one. So whenever we use to SPI, we need to enable whenever we need to use SPI, we need to enable it or disable it. And then we also have SSI config. SSI is internal slave select. So this is used in combination with SSM. And we can basically, if we have a single master, single slave system, we can use this to avoid using the NSS pin, which saves us our one pin that we can use for something else. So I'm going to implement these two, and then we're getting pretty close to having something that looks like it's working, I feel like. Okay. And then probably next time we're on, we can do testing, and we can do testing, and we can do we can do the receive data API, and we can do the testing API. We can test that the code that we've written works. Albeit it's quite easy to test that what we've written works. You just need to do an SPI implementation and walk through the registers. But I've been speaking for a whole hour, and I feel like I'm tired of speaking at the moment. Let me look for questions. I might even do a another stream later today if I feel strong enough. Okay, cool. So let's implement this to peripheral control. That this is to enable and disable, and the other one which is come on, think. The other one which is for software slave management. I'll kind of copy this, and I'll say this is SPI. Say peripheral control, and then second enable is en or di, and or state you want enable or disable. Returns void. Okay, cool. So let's throw this in. Void SPI. SPI. I wanna go here and just copy it. Easier. That way I don't make a mistake. Okay, cool. So let's set that B2 now. If en or di equals to enable PSPI X CR1, I think, and I think we want to do okay. Set, if it's enabled, set the bit for SPI CR1, SPI CR1. Which one is this? SPE. Okay. Else SPI X CR1. And then we want to reset, basically disable. This is 1 SPI CR1. Sick. Terminate. Okay, let's take this and make one more. And this one is going to be SPI SSI on config. Yeah. And then I want to go here. I want to copy this. I want this. I want to go here. I want to do this. I want to do this. I want to do that. I want to do that. And then I can just actually take that, put it there. But then I have to be very careful to make sure that this is not, I do not have SSI, I do not have any leftover coding. Okay, awesome. So what have we done? We basically enabled one to enable SSI, and also we let one be able to use software slave management fully. So this way you can avoid using the NSS pin completely. Okay. Perhaps when we are, let's add a bit more convenience here. We need Let's enable the clock for this peripheral, whichever one this is. Okay, that way we can enable the clock, it can work. And I also think I can do this in, if I'm not wrong, that way it's easier. Let's go to gpio.init. Yeah, also here. Enable clock when initializing peripherals. Cool, that's good. What else? Okay. First of all, let's check comments. No comments, just yet. Okay. Git status. Is this thing building? First of all. Building completely. Awesome. Git status. Git add drivers. Sourcing. No. Git commit. Add options for SPI init. Enable one to use SSI. Enable one to enable SPI peripheral. Enable clock peripheral clock when excuse me. And that's it. Git push. Yeah, 10:30. 90-minute stream. We managed to do SPI all the way to initialization and clocks in. So, if anyone has any questions, now would be the time to ask. Now would be the time to ask if you have any questions. If you have any questions, you can ask now. Remember, we have a Discord community, so you can join us in the Discord community, and that so we are able. So I'm gonna leave now. I'm gonna go get a bigger breadboard so we can have the two devices on one breadboard, and also maybe a logic level. What's this thing called? What's this? Logic analyzer. So I want to have a logic analyzer and both devices on one breadboard. That way I can kind of send data from one device to the other, and we can kind of monitor as we send the data, and we can test and debug. There might be some bugs in this code. I haven't tested it yet, so when we are going to test, we'll find out if there's any bugs and such, and we'll be able to fix them, if that makes any sense. Thank you. Cheers. That's I think that's the one for today, for this morning. I'll see if I'll do another stream later today or later in the week, but I need to finish SPI all the way to interrupts as soon as possible because Marvin wants to use the code to integrate some NFC stuff, and I want to get that done. Okay, cheers. Thank you so much. I don't see any questions. Thank you for coming. And that was our stream today on SPI, initialization, and SendData API. Perfect.